Hello, this is Daniel Collins. Today I'll be presenting on our paper entitled Anonymity-preserving Byzantine vector consensus. This is joint work done also with Cachin, Tyler Crain, and Vincent Gramoli. So consider a distributed survey between n computers, which we refer to as processes. For the survey, we would like fault tolerance, in as much as if a number of computers have crashed or failed or are acting maliciously, we would like the survey to still go ahead. We'd like to cope with an asynchronous network. So if a message is sent to another process, it is unclear how long it takes for that message to be delivered. We want to ensure the anonymity of proposers. So I propose a value, then my identity to the people who receive that message or that value is unclear in amongst the other processes in the set. I would like an efficient protocol, one that terminates in the order of seconds. We'd like to support arbitrary responses to the survey. So importantly, our survey could be anything from an actual survey in which written responses are provided as answers. We could be considering an election in which different identities of potential candidates are proposed without prior setup, things like this. We wouldn't like to trust a third party, and so we will explicitly avoid this. And given these properties and the distributed nature of our problem, we take a distributed systems approach to solve it. So we model processes as either being correct or arbitrarily faulty. We call this Byzantine. In the classic consensus problem, we have n distributed processes. It should agree on the same value. To generalize this, the vector consensus problem was introduced, which posits that n processes must agree on a vector of values, ideally each being proposed by a different process among the set. So we assume that T processes are faulty, T being less than n over 3, which is optimal to achieve consensus in these conditions. And we consider them to be corrupted by an adversary. We want the usual consensus properties of agreement, everyone agrees on the same value, termination, everyone correct eventually decides, and validity, which depends on the formulation. We introduce a new property to characterize our problem, the anonymity-preserving vector consensus problem, or AVC. Namely, we have an adversary, and the probability of this adversary of correctly guessing the identity of someone who's proposed a value, someone, of course, who hasn't corrupted, is at most 1 over n minus t. So if n is the number of processes and t is the number of corrupted processes, then all correct processes, their proposals are mixed together with respect to the adversary being able to determine who sent what. So at a higher level, the way we solve this is we perform a reduction to binary consensus. To begin, processes will anonymously, reliably broadcast their proposal. So we make the assumption of anonymous channels here. This could be implemented internally, or this could be implemented using something like Tor. To ensure that at most one proposal per process is sent, we use traceable ring signatures. We make careful logic to associate a binary consensus instance with each anonymous proposal. We consider our solution to be relatively performant. It has cubic message complexity in usual case execution, also in which 4 message delays are required for termination. This is the same as a recent consensus baseline, which is also a reduction to binary consensus. And it has a constant message overhead relative to this as well. With 100 distributed nodes in 3 continents, our experiments demonstrate that we terminate between 5 and 6 seconds usually. So this problem gives us, seems to be quite familiar in as much as electronic voting sounds very similar to it. So we characterize some of the related work, including some of the potential solutions to electronic voting. Since we require fault tolerance, we require consensus or a trusted third party. So we will not use a trusted third party. Some of these solutions are not distributed And so we can generally assume that an underlying consensus, for example, is used to implement them in this discussion. So with mixed nets, basically the essential idea of a mixed net is you have a set of processes, each of which perform a shuffle, a verifiable shuffle of a set of messages, and if you have enough of them and enough of them don't collude, then the outcome is that you have a mixed and anonymous set of messages. But the problem in the distributed environment, where we have a number O of n, number of processes that can fail, then it's unclear how to generalize to how to make this more efficient, firstly, and secondly, how to actually deal with this with asynchronous network behavior. Homomorphic tallying, in which a homomorphic encryption scheme is used to sum together messages, for example, before they're decrypted. If we have a multiplicative or additive homomorphism, then in some cases this may suffice for a simple electronic election, but with arbitrary ballots or arbitrary values, it's unclear exactly how to encode these. And with fully homomorphic encryption, to come up with an arbitrary encoding, obviously as the encoding becomes more complicated, so does the cost. And so in the general case, this is not ideal. DC nets, based on the dining cryptographer's problem, have robustness issues, unfortunately. Private set intersection is not general enough. If you have some kind of election, say, where you want to, there's some decision to be made, if everyone proposes a certain value, then private set intersection is not unreasonable, but in the general case of the survey, say, it's not tenable. And multi-party computation, again, to encode some kind of general function, it has performance issues. So to model our problem, we consider n processes, which have pairwise, reliable, and asynchronous channels. So reliable in as much as if two processes are correct, then a message sent between them will eventually be delivered at the intended location. And the asynchronity means that the message delays are not known by processes, and so a message could take any amount of time to be delivered. Processes can also use one-way anonymous channels. So in essence, you can think about this like if I were to have a buffer and a message was suddenly to appear in that buffer, it would not be clear who deposited that message in the buffer. For consensus, we need to get around the fact that we cannot terminate with faults in the general case in an asynchronous network, so we invoke partial synchrony to achieve this. So we assume that eventually our process execution time and message delays are upward bounded by some unknown finite constants, unknown to the processes during execution. An adversary we model as controlling message delivery, i.e. sends and receives. He has to abide by the restrictions of the channels, such as partial synchrony, and he is able to corrupt up to T processes who can collude and deviate arbitrarily from the prescribed algorithm. So a traceable ring signature is a signature which takes a ring, a set of public keys generally, as input, and it can take a piece of associated data, which we call an issue. And the idea is that you have a signature, and the signature represents a proof that someone in that ring signed the message, but other than that, there's no information about who signed it. With the traceability of some ring signatures, it's possible that if a process signs twice with respect to the same issue, then their identity will always be exposed. So, say if their public key will be revealed, for example. The TRS comprises three algorithms, which we consider to be distributed oracles, which processes can access. We have the sign oracle, which takes an index, ID, and a message and outputs a signature. We restrict the oracle such that only PI can sign with respect to index I, and cannot obviously sign with respect to other indices. The verification function is standard, and we require that for verification to succeed, a signature and corresponding message and ID must have been input to the signing algorithm. The trace function takes 2 messages and 2 signatures, and also a ID, and outputs a string or a number between 1 and n. So it outputs independent if the 2 signatures were signed by different processes. It outputs linked if the same process has signed the same message twice. And it outputs their identity if the same process signed a different message each time with respect to the same issue. These signatures can be implemented in O of kn space, where k is a security parameter and n is the number of processes. You can do better with trusted setups, for example. We assume the ring is always the same n processes. So we have our set of n processes that's fixed a priori, and everyone's always signing with respect to it. We assume, for simplicity, without too much loss of generality, that cryptography is unbreakable. So we firstly describe an algorithm that replaces message send and receive calls on the reliable channels. In a distributed algorithm, certainly at least the ones that we consider, messages can be divided into types based on the round number, if it's a round-based algorithm, the label of the message, say it's a pre-commit or commit or something like that. And so we assume then that a process invokes send of the message itself and a corresponding identifier for the message to another process. And then instead of sending the message, the process produces a traceable ring signature and then anonymously sends that to the process. So the process confirms the signature is verified. So what the process knows now is that it has received a message from someone in the set of processes. To check whether he's received a message from respect to the same identifier from the same process twice, he runs the trace algorithm with respect to all messages and signatures buffered so far with respect to this identifier. If there's any message that doesn't pass the trace checks, the process ignores the message. Otherwise, it processes as if it had just received a message. We call this traceable broadcast because in our algorithms, only broadcasts are used. And the overhead of this is O of S, where S is the signature size, and this overhead is additive. So the anonymous vector consensus problem, or anonymity-preserving vector consensus problem, is such that there are 2 functions, propose and decide. Propose denotes the input to the function, and decide is the output. So the properties, firstly we have anonymity, the new property, which states loosely that we have an experiment and A is an adversary, and A has to guess the identity of some process. And during this game, he is allowed to receive previous transcripts of that process's executions and subsequent executions, which he can control through oracle calls. So the advantage of this adversary winning is that it most 1 over n minus 2. Standard next 3 properties for consensus are, firstly we have agreement. So if all non-faulty processes, if they invoke decide, then they all output the same vector there. Termination states that all non-faulty processes eventually invoke decide. And validity. So we have valid, which is a deterministic predicate. One example of this predicate could be, say, something that checks a signature and verifies that the signature is correct. But this can be rather general. So we state that firstly, all decided values must satisfy this predicate, and the size of the decided vector must be at least n minus 2. In this, it follows that from our construction that at least v minus t values must have been proposed by different processes. Additional primitives that we introduced for the sake of explaining our algorithm. We assume that all send and receive calls are implemented through this traceable broadcast mechanism. We then quickly state the properties of binary consensus. So value is input and output. In each case, it's a binary value, either 0 or 1. And this satisfies comparable consensus properties of validity, agreement, and termination. Reliable broadcast is another algorithm which we use to build our protocol. So this provides us with 2 primitives, RB broadcast and RB deliver. So two notable properties are that if a non-faulty process, RB delivers the message, then all other non-faulty processes will RB deliver the message. And similarly, if non-faulty process broadcasts a message, then it means that all non-faulty processes will deliver a message. So both of these properties are crucial. So for example, if we don't have the first property, then it could be such that if a faulty process performs something, then it's possible that two different processes will, who are correct, will output two different messages. We also want some kind of unicity property in which at most one message is delivered for each sender who sends and broadcasts a message. This abstraction is weaker than consensus. So namely, we don't require partial synchrony, for example. We require quadratic message complexity and 3 message delays to terminate. So this could be implemented with a classic branches algorithm. So the anonymized vector consensus protocol, which is our solution to the ABC problem, it reduces binary consensus. And so firstly, we describe the reduction to binary consensus as if it were a not anonymous algorithm. So we have proposed at some value. We have a set of processes which we know a priori. And so for each of them, we can associate an instance of binary consensus with them. So we reliably broadcast our value when we start. And then whenever we deliver a value that satisfies the validity predicate, we'll propose 1 in the binary consensus instance labeled I, if we have not yet proposed anything in that. We'll wait until we terminate in n-t binary consensus instances with the value 1. In all other instances that we haven't decided in yet or proposed in yet, we propose 0. Eventually, we'll end up with a vector once they all terminate, containing which we can build, which contains proposals such that the corresponding binary consensus instance, 1 was decided in it. And so that is our vector which we output. We can sort it so everyone outputs the exact same vector. So the main problem here is that if we're dealing then with anonymous broadcast, then we cannot use this labeling technique of assuming that each binary consensus instance belongs to a different process, because no one knows what message was proposal was sent by each process. So to solve this problem, we have 2 main steps. So what we do is we label our binary consensus instances by proposals rather than indices, which we a priori know. Then we, to deal with this, because our algorithm usually assumes, our binary consensus algorithm generally assumes that we know which instance we're talking about, we intercept the send and receive calls there so that we can use those labels, which are now proposals rather than indices, to make the algorithms work as we want. So at a high level, we initially spawn in unlabeled instances of binary consensus, and then we will deposit messages into them and execute in them as we go along. So when a proposal is RB delivered, but that is valid, we will label a fresh instance with prop with the proposal, and we'll propose 1 in that instance. And we'll see how to deal with the messages soon. So one example line from a binary consensus algorithm could take the form, broadcast this auxiliary message in round R, and it's a binary value of either 0 or 1. So an identifier is usually, if we were doing a reduction to binary consensus with n instances, then we would send a different, we would send the process ID that we're referring to disseminate. But we need to handle this differently here. So considering that same example, when we call the broadcast, if the value is 1, then we can broadcast the value. And because we know that we RB delivered the value, so too will everyone else. And eventually they will be able to process the message. If V is 0, we buffer the message. So once we've broadcasted this aux RV in all n instances of binary consensus for the given round, we broadcast a different message containing a set 1s, which corresponds to all proposals, i.e. instance labels, for which we broadcast 1 in, i.e. at step 1 here. So then when a process receives this message, assuming of course the sender is correct, what we can infer is that the process who sent the AUX-R1 message has already broadcast 1 in those instances. And so for all other instances, we assume that it will send 0. It refers to sending 0 rather. So that's how the message will be interpreted. By construction of the binary consensus algorithm that we use, the same concept will apply for all message calls. So this brings us to the question of efficiency of the algorithm with the cryptography that we use and also this replacement of messages. So for an experimental setup, we use Amazon EC2 instances in 3 continents. We simulate anonymous channels with a message delay rather than using the anonymous channels. We make an optimization in which we only need to anonymously broadcast the proposal using the first step of the reliable broadcast algorithm. But when doing this, there are de-anonymization concerns, which we'll briefly touch on. And then in experiments, we compare the n-way anonymous reliable broadcast using this first anonymous step, AVCP, basically the reliable broadcast algorithm plus the binary consensus logic, and DBFT, which is a recent consensus algorithm. So we have 2 major observations. We can see in the first graph that the difference between the binary consensus and the full reduction to from AVC to binary consensus and the reliable broadcast is not terribly different in terms of cost. And the second thing we can see is that by comparison to DBFT, principally due to the cryptographic overhead, that AVCP is more expensive. But even with 100 nodes, as we see, we can terminate between 5 and 6 seconds. To discuss a bit before concluding, we avoid a leader-based consensus algorithm, such as PBFT. One could imagine when using such an algorithm that in order to coordinate, a leader will propose a set of values for which it was either decided on or the leader has changed. And so if that leader has given n values to satisfy validity, all they need to do is choose n minus t of them. And so they could choose n minus t of its choice, which could be quite bad in certain situations. To avoid partial synchrony, we can use a randomized consensus algorithm. We can combine our protocol with threshold encryption. So threshold encryption is basically encryption in which is performed by everyone. And so with 1 extra message delay, we can achieve the functionality that proposed values are hidden until after termination. We combined anonymous channels with regular channels in our experiments. But to do this, we need to be a bit careful because it's possible that someone could associate, say, a slow process in anonymous channels with a slow process using regular channels. And so they could correlate and gain information about which process is sending what. So ideally, we want to minimize this correlation. So to conclude, we have defined and solved the anonymity-preserving vector consensus problem. We've presented an efficient solution asymptotically and also experimentally using geo-distributed nodes. To propose some research directions, one interesting direction, in my opinion, is to explore fault tolerance and efficient anonymity. So you have a set of Byzantine processes, and say you want to perform n-way reliable broadcast. And so to do that in an efficient way, say a constant message step overhead, would be nice. Different and more efficient constructions are obviously always welcome. And to add an accountability/fault detection layer on top of, say, this algorithm could increase its robustness in case of practical usage. Say, for example, you can tell who's been faulty, given the class of faults you're dealing with is detectable. And so with that, we conclude. So we thank you for listening to this talk. We'll take any questions by email or any other forum if necessary. And we thank you for your time.